Hey guys, I wanted to walk us through how to do the general steps of ionic bonds before we get started with today with the activity of the jigsaw puzzles and just identifying what's happening just in general. So, if we remember first and foremost that we have this imaginary line that separates our metals from our nonmetals, right? We have our metals over here, we have our nonmetals over here. Remembering that hydrogen is that one exception where it really belongs with the nonmetals, but we kind of ignore that for the purpose of where it's placed based off its reactivity and its placement just in general on the periodic table. Now, if we think about the metals are over here on the left-hand side. And if we remember, basically, all of the elements that we care about are going to be the ones without transition metals, without this wonderful section right here that likes to mess us up, right? So we really care about the ones where we know the valence electrons, right? So we look at this first column has one valence electron. The second column has two, three, four, five, six, seven, and eight way over here, excluding again our another wonderful exception where helium only has two valence electrons, right? Remember, our octet rule tells us that our maximum number of valence electrons is 8. So everything's goal is to get to 8 or in opposite 0. Okay? 0 is essentially just getting to 8 or lowering its valence electron shell so it gets to 8 backwards. But we just remember it as getting to 8 or 0 because otherwise it gets too confusing. It kind of doesn't make as much sense. So we're going to ignore that. 8 or 0 are magic numbers. And so we tend to look at our metals, the left side, are closer to 0. And therefore, they want to lose all their valence electrons. They want them to go away. Our nonmetals are closer to 8. So they want to gain extra valence electrons. They want those extra ones. They don't want to have any missing. Okay, so if we remember way back to reactivity, I know it's coming back, right? Elements that have less valence electrons are more reactive if they're a metal. Elements with more valence electrons are more reactive when they're a non-metal. Okay, we can also talk about the atomic radius, remembering that the larger the atom is, if it's a metal, the more reactive it is. The smaller the non-metal is, the more reactive it is. Also, if we don't want to forget, this last column are our noble gases. They already have 8, or in helium's case is 2, but they already have a full valence shell. They're not going to mix with anything because they're already happy, they're already stable. They don't want to talk to the other elements. They're going to hang out all by themselves. So now we just really worry about the rest of the elements. So we remember way back to when we talked about those ions, right? We talked about something like I love sodium, my favorite, as we all know from, the fire alarm. Sodium is Na, and it's in that first column, which means it has one valence electron, right? And then we have stuff over here on the right side of the periodic table. And these ones, let's pick chlorine just because, we talk about chlorine a lot, right? So elements like chlorine has 7 valence electrons. So we go 1, 2, 3, 4, 5, 6, 7. Right? Sodium is super, super close to having that one valence electron to go away. Chlorine has 7, which means it's super close to being happy, to being stable, to be full. Everybody wants to have either 0 or 8. So what's going to happen is these two elements like to mix together. They like to interact with each other so that both of them can become happy. To do that, sodium has to give away its electron to chlorine. And if it does that, sodium becomes that ion. Remember, this is where we got a little bit tricky when we talked about it way back when. Sodium, if it loses a valence electron, it has one less negative charge because our electrons are all negative than it has positive charges. If we look at sodium, sodium has 11 protons and it had 11 electrons, but now it only has 10, which means it now has a positive 1 charge because it has one more positive proton than negative electrons. At the same time, chlorine now has an extra electron, right? It gained that one extra electron right there from sodium. So now chlorine has that extra one, making it have 18 electrons, but only 17 protons. So it has one extra charge, making it a -1 charge. Now, if we look, those two charges, what number do they add together to make? They add together to make 0. And because they add together to make 0, they're going to create what we call an ionic bond. When our charges can add to 0, our bond is created. Okay? So every time we do something where we want to have elements mixed together, we have to make sure that we have the same charge or the same overall charge by the end. We want our charges to add to 0, right? We want to see this positive one and this negative one equaling 0 by the end. So if we look at all these, right, we're looking at the metals and the nonmetals, right? We can look at them as almost like puzzle pieces. So if we look at something again like sodium and chlorine, okay, we have our sodium, which can lose an electron. That's why we have this empty space right here, right? If we look at those puzzle pieces, it has an empty space because it's when it lost an electron. And again, reminder that that's what this +1 comes in, right? The +1 means that it lost an electron. Right? So it could gain that extra charge, and so it could be more stable, to be happier, right? Because sodium, when it's not stable, when it's by itself, when it's element sodium without a charge, that's when we explode things. That's when we create the fires, the smoke, the fire alarms go off. Okay, but this one, chlorine likes to bond with the sodium. So to bond it, we're gonna have the puzzle pieces match up, right? And so if we bring those puzzle pieces together to form that bond, we can see that chlorine gained an electron. That's why it kind of has this extra space right here where the sodium gave its extra little bit to chlorine to make it happy, to create that final compound where we have one sodium and one chlorine. That's when we write the compound of sodium 1, 1, which we're not going to put the 1 there. We're going to take it back out because we don't need the 1 if it just says 1. So sodium and then chlorine. Again, we don't need to put the 1 down here either, but it's nice to remember that that's what it means when we put our compound together and we get sodium chloride. All right. Oh, this should say chloride, not chlorine. I am so sorry. That should say chloride. And it says chloride because of the compound. When it's a compound, we change the ending to IDE. So that's why you see on all those puzzle pieces, it says IDE because the chlorine became an ion when it lost its electron, or sorry, not lost, it gained an electron. I apologize, I forgot. So when it gained an electron, it changed the ending, right? Gained an electron. The ending of chlorine changed from INE to IDE. Okay, and that's just to tell us that the element is now in a compound. It's not all by itself. So that's the only reason you'll see these formulas written in a different way than you're used to. Okay, so now that we know that, okay, we can take a couple other practice problems, right? We've looked at sodium, right? We've looked at chlorine, but maybe let's look at chlorine again, right? Or let's look at a different element, okay? Sometimes we're going to have an element like potassium. Potassium is way up here as well, and potassium has how many valence electrons? Well, if it's in the first column, it has one valence electron. So we can go ahead and look at potassium. Okay, potassium is right here. And so when is gonna become an ion. It's going to lose that valence electron the same way sodium did, and that's why it has a +1 charge. Then we could have something like oxygen, okay? A puzzle piece such as oxygen. Oxygen is way up here. Oxygen is number 8, and it's all the way in the 16th column, which means it has 6 valence electrons. Okay, oxygen, in order to become happy, wants to gain 2 valence electrons. So if we put these puzzle pieces together, right, oxygen's going to come over here. It's going to hang out with potassium. But if we notice, potassium is happy, right? It doesn't have any extra spaces that it hasn't used up. But oxygen's got this whole section right here. It's sad. It's not happy yet. Right now, it's only gained 1 electron from this 1 potassium, right? And oxygen is never going to do that. Our elements don't ever just gain half of what they want. And we have to remember that there's a bunch of different elements of potassium and oxygen. If they're trying to combine, there's a bunch of them just hanging around in an area together. And so when they combine, it's never just going to be just the amount that it wants. It's always going to be the amount that it wants. So it's going to be a second one that we can bring in here to make 2 potassiums. So it balances out the oxygen, right? So we always want to make sure we're balancing out both sides, right? So the other thing we want to make sure that doesn't happen is, I'm going to remove this for a second. We don't want to ever bring in a second metal that's not the same one as before. So if you guys look, we have potassium and sodium now, and that's not something we're able to do. And that's because our metals aren't going to mix together like that on a regular basis. It does happen if you put in a lot of extra things and do a lot of extra stuff that we're not going to worry about. For what our purposes is for chemistry class, this is not happening. So we never want to bring in a second metal that's going to mess us up. Same thing with our nonmetals. We would never bring in an extra nonmetal from a different element. So instead, we end up with 2 potassiums to balance out our oxygen. And when this happens, we have, again, because it's becoming a compound, it's an ionic bond. It's when a metal and a nonmetal mix. It's no longer oxygen, but it's going to turn into oxide, which is what it shows on your little pieces of paper. And so we can count that we have 1, 2 potassiums. So we're going to have K2 for 2 different potassiums. And then we still only have 1 oxygen. So we're going to leave it as O. Remember, we don't want to put this 1 there because the O by itself tells us that it's 1 oxygen, right? So we're not going to put this part there. But we can remember that it's 2 potassiums for every 1 oxygen. The big thing is we do need to put this 2 right here, right? It's different than the 1 because if we just put KO, in my head, I'm thinking we have 1 K and we have 1 O and those are together. But that's not allowed to happen. So we have to make sure we put this 2 down there to signify how many Ks we're looking at. All right. Last but not least, let's take a look one more time at another element combination. Okay. This time let's look at aluminum. So now aluminum is even a little bit trickier than the rest. Okay, because aluminum is way up here. Aluminum is way over here and it has 1, 2, 3 valence electrons. So that's why it's going to have a +3 charge because it has 3 electrons it wants to give away. That's why it has 3 open spaces. So if we wanted to combine it with something like oxygen, right? They fit together pretty well, right? But there's still that extra space that's not there yet. Well, so that means we need to bring in another oxygen because remember, we can't bring in any other element for our nonmetal side unless it's more oxygens. So we're going to put another oxygen in there. But now if we look, we've messed up the aluminum. Okay, so that means we have to go back and we have to get another aluminum and we got to bring another aluminum in. So now we're going to put in another aluminum. But when we do that, that doesn't give us enough space to finish out our oxygens. So now again, we got to bring in another oxygen. So we got to find another oxygen puzzle piece. And when we do that, we finally have enough. But then that means we have one, two aluminums. So it becomes Al2. And we have one, two, three oxygens. So it becomes O3. Now, if you remember way back to the beginning, I talked about how we have to make sure our charges add to zero. That's something we can look at again here real quick when we look at our aluminum oxide, because remember oxide, because it's a compound. If we look, we have aluminum with a +3 charge, and we have two of them. Okay. Now we have oxygen with a -2 charge, and we have three of them. I'm sorry. And so now if we look, we have a total on the positive side of 3 plus 3, so we have a +6. And we have a total on the negative side of -2 plus -2 plus -2, so -6. So we have an overall charge of 0, right? That's what we want and is our end goal. We always want to end up with 0 by the end. And that's to make sure that our charge is balanced. That's basically to make sure that we have the puzzle pieces, that those all match up, right? We want to make sure that there's no empty spaces, there's no extra juts out, there's no extra teeth on there. We want to make sure that our electrons have somewhere to go and we have enough electrons on the other side. Right? So that's the gist of what we're trying to do here, right? We're going to come up with these reasons for why the electrons move, and we're going to end up with writing out these formulas. This is what our end product we want to look like, right? So you're going to come up with some more that you're going to practice on your own, right? And then if you have questions, go ahead and make sure you reach out, all right?